Hey guys, well, I'm not gonna lie. Pretty much blew through my semester's worth of special effects in that last video. So today we have a little red bucket on a string, and that's about it. But we're out here in this beautiful location. We are right by the beach, and since this is our last discussion about the shoreline and we're gonna talk about tides, I figured, what a great place to be as the weather warms up a little bit. So what the heck does a little red bucket and a string have to do with tides? Well, let's see if we can't figure that out. So I have a little bit of water in here, and you guys may already see this coming, but if I take this bucket, hopefully, and I start swinging it, the water stays in there and it doesn't come out. Well, why is that? All right, well, what we need to do is figure out the forces acting on this bucket. So I'll have to slow it down. So what I'm gonna do is I'm gonna slow this bucket down a little bit. Okay, not that much. That's a little bit much. We needed to go a little bit faster than that. There we go, okay. All right, so this is better. So what we're gonna do is we're gonna look at the bucket that's moving around, all right? And there are forces acting on it. So the first one may seem pretty obvious. We have a string, and that string is keeping that bucket from going somewhere, right? So there's a force down on that string. We'll just call that big F for now. Well, something else is that the water in there is staying put. Right? It is staying against the bottom of that bucket and it's not coming out. If you guys have ever been on a carnival ride, one of those ones with Gravitron or something like that that spins you around, and you can feel that you're pushed against that seat. And that's sort of what's going on right now. That water is being pushed up against the bottom of that bucket. But here's something really weird. There's no force pulling that water up against that bucket. Let me see if I can explain what I mean here a little bit. So the only force acting on it right now is that string. So if I take this bucket and I let it go, and I remove the force of that string, what do you think is going to happen? Well, let's find out. So bucket's moving around, and what I'm going to do is I'm going to release that force when the bucket gets to the very top of this circle. So here we go. It went sideways, right? It went that way. It went tangential to this circle. It didn't go out. So while you may feel like you're being pushed up against the back of that carnival ride and the water is pushed up against the back of the bucket, the actual movement is to the side, and it's always like that. In fact, I just realized I got rid of my bucket. Kind of need that back. Okay, I'll tell you what, one more little bit of special effects, and I promise that's gonna be it. So here we go, let's bring it back. There we go, okay, we now have our moving bucket again. All right, so anyhow, we have our big F towards the middle. And now we know that there's some sort of velocity that's to the side. So I'm gonna go ahead and put a V there, right? And that's all the way around. No matter where I were to release the string, the bucket would wanna go tangential to this circle, right? So obviously released at the top, it went that way. At the bottom, it would go this way and so on and so forth, and you can see that. Well, what's really going on, what this V does is it gives this mass, right, this bucket and this water, something called momentum. And that's just its mass times its velocity, that V. And there's another thing at play here, and that's something called inertia. And inertia is the resistance to a change in that momentum, all right? So what you have is a momentum along that V, and then that force, that F, where my hand was, pulling on that string, is giving it little corrections. So it wants to keep going straight, but that force keeps forcing it to turn a little bit. So it creates this circle, all right? So that apparent force of being pushed back into the bucket is really a force towards the center. And what does this have to do with tides? Okay, yeah, fair enough, right? Well, as you guys may have figured out, that force, that F, is gravity, all right? So this is gonna happen between bodies in space. So we already talked about gravity as the acceleration of all things with mass towards the Earth. Well, as it turns out, when you move away from Earth, it's actually an acceleration of all things with mass towards each other, all right? And that force is proportional to the masses of the objects and the distance between them, all right? And so you can sort of think of this, we'll take our bucket and a string now and think about the center of that as the Earth, and that bucket moving around is the moon, okay? So the moon's in orbit, you have gravity attraction actually between both the Earth and the moon, and you have that momentum carrying the moon around so that nary the twain shall meet. The moon's not going to collide with the Earth, regardless of how big that gravitational force is. So this is starting to get us there. But there's something else really interesting that actually creates tides, because just gravity alone is not going to do it, right? You would just have a single force acting on the whole Earth and we wouldn't get these tides. So the other thing to note, like I said, that gravitational force is proportional to a distance, but there's something else, right? Gravity doesn't act the same at all points on this bucket or the moon or anything like that, right? So the face of the bucket, in this case, the opening towards the center, towards my hand, has a stronger gravitational force than the outside, so it changes. And this is actually something akin, or actually part of general theory of relativity, if you've heard of Albert Einstein, all right? And what we have is a field of gravity, not constant. Let me see if I can explain this a little bit better. So let's actually go ahead and get rid of that bucket again. There it goes. It's fine over there. We won't need that. And the reason I want to talk about this is because both the moon and the sun affect the tides, and they do it differently. And although the sun is incredibly massive and the total gravitational force between the Earth and the sun is much bigger than the moon, this difference in force is really what matters. So let me give you an example of that. All right, so let's say we're out here on the beach and I have a massive bonfire. Okay, massive, not that massive. That's better. All right, so what happens is I'm standing here, right? I'm warming myself, it's nice and warm. Well, if I move, let's get all the way extreme here. If I move from here to about here, things don't change that much, right? It still feels about the same amount of heat, right? It's pretty warm, but it's not a big difference. Well, let's say I have a smaller fire. Let's say I have a fire here. Okay, I swear this is the last special effects I'm gonna do anyhow. A smaller fire. Well, if I put my hand this close or this close, there's gonna be a pretty big difference in the amount of heat that I feel, all right? It's gonna be much hotter here until I pull it away just a little bit. So even though that fire is much bigger, the fact that I'm closer to this one means there's a bigger difference when I move away. So again, what does this have to do with tides? Well, this has to do with that gravitational field I was talking about. So what happens is you can think of gravity, that force of gravity, as the intensity of the fire, right? That heat. And the sun is much further away, but if you're on one side of the planet or the other, it's not going to matter that much. There's not going to be a very big difference in that force. But something like the moon, that smaller flame, right? One side of the Earth to the other makes a bigger difference. And this is called a tidal force. Go figure, right? This is about tides. And that tidal force is what creates those differences. And what this tidal force does out in space, all planetary bodies, is it actually tends to elongate them, right? It tends to make them football shaped because the side closest to that extreme gravity is being pulled much harder than the stuff on the other side. And our inertia, right? That momentum, that inertia, that resistance to change is acting on the entire thing. So if the entire Earth wants to move in one direction and gravity's a little stronger on one side than the other, you're gonna start to get that elongated. And when we come back after I get off the beach here, I'll show you that in a little more detail. But that's what I want you guys to take away from this, okay? So orbit, orbital geometry, gravity, all that good stuff. The important thing is we have an inward force of gravity attracting two bodies, and we have a tidal force. That means the side closest to the gravitational force is stronger than the outside. So you guys think about that. We'll regroup. The sun's about to set on this beautiful day, so I'll meet you guys back inside and we'll see how this relates to tides on our planet. As we continue our discussion about the coastline, we're now moving on to tides. And you guys may be familiar with these, right? You take a look, you go outside. At one time, the water level might be pretty high on the shore, and another time it might be low. And this, is a slow process that happens throughout the course of a day. Well, this may not seem like a massive change to the coastline. It seems very gentle. But if I take this photo here, this video here of the tides going in and out, well, if I speed it up, you can see that this actually can be a very dramatic process on the coastline. It can wear away at rocks, right? The water actually can move sand around on the beaches. Because we tend to think of things in, our day-to-day lives, but on a geologic scale, this is actually happening incredibly, incredibly fast. So what we're going to do is we're going to figure out, what tides are, where they come from, and just how they affect the coastline. So a few things we got to get through is, what do I mean by some of these definitions? So if I take a look at this picture, which you guys have seen before, this is our rocky intertidal zone, right? One of the communities that we're speaking about, and we have out here in Rhode Island. And we already know that they exist in this intertidal zone between, low tide and high tide, okay? And these are some of those creatures that are sometimes covered with water and sometimes not. All right, well, I keep saying intertidal zone, so let's figure out what this actually means. And the tidal zone is just the difference between the high tide and the low tide. So that's it. That is our tidal zone, all right? This is that zone where the tides affect the coast. And there's a couple other terms. So if the tide is coming in, we call that a flood tide, as that water level moves up and the water moves in towards the coast. And then as the water level comes out, we call that an ebb tide. So the flood and ebb of the tides. Okay, well, we kind of already know this. We see the water level come up and down. But what the heck does a bucket on a string and gravitational fields have to do with this? How does that make this happen? We'll see if we can figure that out. So first thing is, if we take a look at Earth, right, standing out all alone here in space, we know that this isn't true. There's other things acting on it. And the first thing we're going to talk about, and a lot of you guys already said, was that that the moon has something to do with the tides, all right? And that's why we started talking about gravity. So in this case, we already know that, based on earlier, that gravity is an attraction not just to Earth, but between anything with mass, or bodies in space with mass. So from the Earth, there's a gravitational attraction of the moon pulling on that, and the same goes from the moon towards the Earth. Well, something else interesting. So you guys may think, obviously the moon revolves around the Earth. Well, sort of. They actually revolve around each other. It's not just the moon going around the Earth. In fact, they revolve around each other at a point about right here, all right? Below the surface of the Earth, but it's still a point. So instead of thinking about the moon just traveling around the Earth, you can sort of think of this as, two buckets on two strings traveling around that center of your hand. So they're going around, and this is that center. Well, what that means is, yes, there's a gravitational attraction, and we're actually just going to stick with Earth here. So there's gravity from the moon pulling on Earth, but there's also inertia, okay? Momentum. Both of them have it. So there's that attraction towards each other, right, the string, and then there's that inertia, that movement that keeps them from just colliding into one another, because this is a very strong gravitational attraction. So those are the two main forces acting here. And the way this plays out, if I take and I put a band of water around the Earth, so I'm just taking that ocean and I'm expanding it, that's that blue film you see there, and I say, okay, well, what's going to happen? Well, we also know that gravity doesn't necessarily act on a center point. It's not just the center of the Earth and the center of the moon pulling towards each other, right? This is where I spoke about that field. So we already know that the gravity on this side of the Earth is a little bit stronger than the center than the other side of the Earth. And what this means is, because the Earth isn't going to deform, right? It's pretty solid. And it does a little bit, but not perceptibly. The ocean is. So what happens is that gravity pulls from the moon, it actually stretches the ocean out, creates almost like a football shape. The reason for that, again, is you have the strongest gravitational pull right here on this side towards the moon. And then actually you have the Earth being pulled a little bit too. And it's being pulled away from the ocean on the other side. So it's not that something's necessarily pushing the ocean out. It's just that the Earth is being pulled a little bit away and the water's being pulled a little away because of that field, because of that difference in the strength of gravity from one side to the other. So you end up with, again, this oblong shape of water around the surface of the Earth. Well, okay, how does this, again, what does this mean for tides? Well, I'm going to draw an imaginary line around here. So this dotted line represents, if we had nothing else, everything was stable, this would be the flat ocean around the Earth. Well, if I take that line and I stretch it out straight, so I'm just taking that circle line and I'm making a straight line. And if I look where I started here, where did I start? I started right here where that dotted line meets this curve of ocean. And that's we'll call that our 0 point. Well, if I look a little bit ahead, let's say I look at this point right here. And that, you'll notice, is the point where the ocean is the furthest away from that line. So what that might look like is a curve like this, a curve up. Okay? Well, if I choose another point, let's choose this next point down here where we hit 0 again, right? So it's almost like the ocean comes right back down to that level surface. So I'm going to do that up here on my diagram, and I'm going to get 0. Maybe you guys see where I'm headed with this. So let's choose another line. Let's choose the next point that's right there where the ocean is the furthest below our 0 line. And what we end up with it is a curve like that. Well, if we keep doing this all the way around the planet, we'll take one more line here, bring it back to 0. What does this look like? It looks like something we've already talked about. So if I do this all the way around, we get something like this, right? We get a wave. And as it turns out, tides are just the longest of all ocean waves. And they are waves that have a wavelength of half the circumference of the Earth. Okay, about 12,500 miles is one wavelength. That's quite a bit. And just like we defined our waves, each point at the top is a crest, and at the bottom is a trough. And like I said, this 0 line, our flat surface, is just now the flat surface of Earth if no gravitational pull from the moon was acting on it. And that's what you get. Tides are the longest of all ocean waves because they create this bulge, right? And it ends up looking like that, looking like something you guys already know. All right, well, that's not just the end of it, right? How do we actually get the rise and fall? How does all of this work? Well, something else we know is we know that the moon doesn't work alone, all right? So we know there's a sun out there. We know there's a really big sun out there with its own gravity. In fact, the gravitational pull of the sun is so much more than the moon. But if you'll remember back to the discussion we had earlier about that field and about how close you need to be. So you remember that fire that you're really far away from, or that small flame that you're a little bit closer to. And you can sort of think of the moon and the sun like that. So the sun is that giant fire off in the distance, and the moon's a smaller flame a bit closer. And I'll show you what I mean by that. So what I'm going to do is I'm going to take this bulge based on the moon. I'm going to make it a little bit bigger just so we can see the sun. So all I'm doing is growing this so you can still think of this bulge here as the bulge of water based on the gravitational attraction of the moon. Well, as it turns out, the sun has its own bulge as well. So I'm going to put that one up here as a smaller, lighter bulge. And the reason it's smaller, again, is because of that field. So while the total gravitational pull from the sun, or actually on the Earth towards the sun, is greater than that of the moon, the difference between this side of the Earth and this side of the Earth is not that big because the sun's so far away. So what that means is the sun pulls a little bit on this side, it pulls the Earth a little bit away from the far side, just like the moon did, but just not as much. So that's something key to remember. The effect of tides from the moon is greater because the moon is closer, all right, regardless of their masses, even though mass has a lot to do with the total gravity. So just keep that in mind. So now what you'll see here is the moon and the sun work together to influence tides. And when they're working in a straight line like this, okay, the sun and moon and Earth are all in a straight line, these bulges correspond, these high tide bulges add up. And this is where you get something called a spring tide, right? The highest of all high tides and the lowest of all low tides over here. Well, if that's a spring tide, let's fast forward a little bit and let's put the moon at a right angle from the sun. Well, now what you'll see is that moon bulge has moved. And while it is still bigger than the sun, it's gotten a little bit smaller because they're not acting together, right? And this is something called a neap tide. All right, this is when the moon and the Earth and the sun are at a right angle and they're not working together. They're not fighting each other. So what you'll notice is now you end up with, a high tide here and then a somewhat low tide and then kind of a high tide, and then so it gets a little complicated. So this is the first thing we're going to start to step through the different types of tides. So far we've discussed something called the equilibrium theory of tides. And this is everything else aside, if just the gravitational effect of the moon and the sun and the geometry were the only thing affecting tides, we would have a very predictable high tide, low tide. We'd know exactly when all of these are going to happen, and they would happen the same all over Earth. But this assumes a few things. All right, number one, it assumes that everything's the same all over Earth, right? It's just a perfect sphere sitting out there in the middle of nowhere, and we already know that's not true. So let's figure out what these differences are. The first difference is, if I back up and we're just going to pay attention to the moon here, and we say, okay, yes, we know that the moon revolves around the Earth. Okay, so we know that the moon moves around, and as it moves around, this tidal bulge will follow, okay? Well, and what you'll see is, here's a high tide, and as it moves over, it brings high tides to the rest of the Earth and low tides as well. However, that's not what's happening, right? How long does it take the moon to go all the way around the Earth? Well, it takes about a month. So what's really happening, let's take one day, right? The Earth revolves once, all right, in one day, and the moon moves that much. It barely moves at all. So the first thing to note, what's really amazing is it isn't so much that the water is moving up and down, it's that we're traveling underneath it. So yes, it is a wave, but you can almost think of it as just this static wave that we're moving through. All right, so I'll show you another picture here in a minute, but the point of this, the really important thing to remember is, let's say, and the entire time that the moon takes to travel around the Earth, well, the Earth is spinning like crazy, right? It spins about 28 times, right? A lunar month. And then what this means, like I said, if you were standing with your head, the moon right above you, and you were at a high tide, throughout the day, you're going to move underneath this bulge. So you're going to start underwater here at the high tide. A little while later, you're at a low tide. And then a little while later, you've moved through another high tide. You guys kind of see the point. And you end up back at the top. So two things here. The first one is, yes, you're moving underneath this wave. It's not the wave moving over you, and that's the tide. The Earth sort of catches up to these bulges and dips, so the crests and troughs of the tidal wave. That's a terrible term. I shouldn't use tidal wave. That's a whole other thing. You guys know what I mean, through the tides. The other thing you'll notice is, well, the moon did move a little bit. So a lunar day, right, the point where your head would be at the same spot under the moon, is about 50 minutes longer. It's just a little bit longer. So here's that first two things that really start to make these tides different. The first one is that, well, if the Earth is rotating underneath this water, if you guys have ever, moved your hand through water, you know there's resistance there. It's not smooth. And the equilibrium theory of tides assumes that everything happens instantaneously, right? As the Earth's turning, that tidal water just stays put and we get instant high tides and low tides, but that's not true. There's some friction. The water can't quite catch up to the Earth ever. It's in this constant state of catch up because the Earth's surface is actually pulling back some of that water. Another thing is that the moon is not exactly straight across on the equator of the Earth. It's at an angle. So what you might end up with if you're on this island here, you're starting at a relatively high tide, then you kind of rotate and you end up here in this sort of weird middle low high tide and then a not quite so low tide. And anyhow, that gets complicated. Not only that, but the moon doesn't stay put. It will actually vary a little bit in its orbit. So now we have three things, right? We have that friction of the water on the surface of the Earth, keeping things a little bit out of whack. We have the fact that the moon's a bit off center, meaning these bulges are hard to predict, or at least they're not exactly in the same spot. So different points on Earth will experience different high tides and low tides. And we have the fact that the moon moves. And this is starting to get into our dynamic theory of tides, okay? And this theory takes into account the physics of gravity and that geometry, but then adds these other things to it to start to explain why tides aren't exactly the same everywhere. What this means is just that. On Earth, tides aren't the same, all right? So this is a figure showing you, based on the colors and the coast, it's just showing you that we have different tides. As an example, let's say up here where we are-ish, right? So Cape Cod, but we're up here in Narragansett, and that's that green, that's semi-diurnal. And semi-diurnal means we have 2 high tides and 2 low tides per day. And you guys can see that if you go out. Well, if you go out and stand for 24 hours and stare at the ocean, you can. Or you can just look it up all online and you can see when the high tides and low tides are. But that's semi-diurnal, all right? 2 high tides and 2 low tides. Well, if you go someplace, what is this, Mobile in the Gulf of Mexico, you end up with diurnal, just 1 high tide and 1 low tide. And then in other places on Earth, these red places, you end up with a mixed tide. So sometimes you have a really high tide and then a somewhat high tide and then a somewhat low tide and then a really low. Anyhow, you guys again see what this is. It starts to get complicated, and this is part of that dynamic theory. And what's really cool is the way these operate is not just linearly, right? They don't just sweep across the Earth, and you can see this because we have a different tide on one side of a continent than the other. And oh, by the way, you know, there's continents there too. So this nice bulge of water has to contend with things in the way. But because of this, the tides operate really interestingly out in the ocean. So this is a figure of something called an amphidromic point. So each one of these centers of what these look like spider webs, right, here is an amphidromic point. And what this means is it means the water actually circulates around that point. So these points out here in the middle of the ocean, right, actually have no tides. They stay at the same level. And the water moves around in a circle. And the colors here just mean where you get some extremes in tides. The darker reds here are the highest high tides and the lowest low. And this is just all over the planet, regardless of spring and neap, because of this geometry of the way these things work. So this is just kind of a neat figure here. It just kind of shows you how that water rotates. So their little red dots are those amphidromic points. And throughout the day, this water rotates around. And maybe if you guys sit here and stare at it long enough, you'll start to see why we have semi-diurnal, diurnal, and these mixed tides, because it doesn't all operate the same. So like I said, you can think of each one of these points as, if you guys have ever gone out, I mean, I don't know if any of you have ever panned for gold or anything like that, but you get a dish of water and you'll start to swirl it around. So in an ocean basin, it can start to look something like this, okay? So we're just gonna take this as our ocean basin of water. In the very center is our amphidromic point. And again, that water sloshing around in these basins, creating high and low tides on the edges, but keeping the center the same, all right? So a side view is gonna look like this, all right? So like I said, that node, right, that amphidromic point stays put, and the water goes this way and rotates around that point, giving you high tides and low tides. So what this means, all of these things combined, we get tidal patterns in different places. So this one, again, is New York, so this is similar to us. This is gonna be that semi-diurnal tide, 2 highs and 2 lows a day. And then you go someone like, what's this, Adelaide, Australia, and this is definitely a mixed. It's different. Also, what you'll see is we do have, you know, spring tides. We have the highest high. Neap tides, we have the lowest high. But in a place like Adelaide, they're much, much bigger. Just look at the sizes of these spring and neap tides. And like I said, it's a bit of a mix, so there's some jagged edges there. And that's how all of these things combine. So this, you know, depending on the coastline, you're gonna get a very different effect. So, you know, again, while we think of this stuff as occurring slowly over a day, if you go back to that film I showed you where we sped up the tides, just realize that in a long duration, a place that has a semi-diurnal tide is getting twice the bombardment of water shaping its coastline than just a diurnal, and so on and so forth with, you know, the difference in these. So that brings us to the end of this module. It was a short one, but a very important one. We talked about a lot of these processes. And we did this all by starting to talk about the coast, right? Where humans experience the ocean, where you guys primarily will experience the ocean and can do it every day because of where you live. And that coast is that entire area, you know, all the way from these waves and tides, all the way through the estuaries and some of that river input. And we know the coastline changes. So take all of this stuff that you've learned. If you're gonna take the exam, you know, make sure you're studying for it. But even if you're not, you know, keep up with those homework assignments and do your reading. And by all means, please come and see me if you have questions. And I will see you guys next time when we get into our last module. So stay tuned and I'll see you in a bit.